All right, this is Physics 1C for March 25th. Today we're going to be talking about the effect of temperature on the flow of electricity and resistance. So we're going to be talking about three different types of materials today. We're going to talk about conductors, which we've discussed before, and the effect that temperature has on them, as well as semiconductors, and then we'll talk about superconductors, which are a kind of newer type of material that we've kind of really only discovered in the last 100 years or so. So, let's get started. So we talked yesterday about electrical resistance, and to remind you what it is, we said that there's a relationship between the potential difference that's applied to a piece of metal or a circuit, which we call delta V, the current that's flowing through the circuit, which we said was the rate at which charges flow, kind of like a rate of change of charge within a circuit, or just the rate at which charges flow, and you multiply by resistance. So this is the thing we're going to be talking about today is resistance. So resistance is something that will reduce the size of current, and it can be used to basically kind of convert electricity from electrical energy into thermal energy. In the case of like an incandescent light bulb, you have a little filament that glows really hot, and then that gives off heat, and it also gives off light. We can also use resistors to make things like toasters and electric stoves, and then resistors are also found inside of radios and computers, of course, too. So it's a very kind of important component in controlling electricity. But one of the things that also affects resistance is how hot an object gets. So to get an understanding of why this is the case, the thing that makes a resistor heat up is basically when electrons try to pass through a material, you have a lot of kind of fixed nuclei. So imagine that you've got, let's say that this is a metal. Metals tend to form kind of somewhat regular lattice patterns. So I'm just going to draw kind of a grid in here where each one of these little dots right here is going to represent a nucleus. So that's what each of those represent, nucleus. And then I'll have some electrons that pass through here. So let's say these little dots are electrons. And let's say that we apply some type of a potential difference to this little piece of metal that we have right here. So we have a piece of metal, we hook it up to a battery. And that's going to cause electric current to flow in this direction. And then back to here. And then current will basically flow in this direction through here. Now these are actually electrons. They're going to flow in the opposite direction of the current. But what happens is that they're going to tend to kind of interact with the nuclei here as they're flowing. So some of them are going to kind of tend to hit these nuclei. What that's going to do is it's going to make these nuclei, which already have some temperature. Let's say that this piece of metal was at room temperature, and while at room temperature, these little atoms are kind of oscillating around. When the electrons interact with them, they start to oscillate around more. And as a result of that interaction of the electrons with the material, the temperature increases. So the vibrations of these molecules gets converted into what we macroscopically call temperature, and there's trillions and trillions and trillions of molecules inside of here. So that's part of what a resistor does. But if you think about it, what if you were to externally heat this object up? So if you add heat in some way, maybe you take a lighter and you put it up next to this piece of metal, or maybe you bring in a space heater or something like that to heat it up. Well, heating this thing up is actually going to make it so that these molecules are going to vibrate with larger vibrations. So if they were vibrating with an amplitude of, like, let's say, I don't know, like this distance before you heat it up, when you heat it up, they're now going to kind of occupy a larger spatial volume. They're going to be vibrating more, right? They're going to have larger amplitudes of vibration, which means that the probability that a electron is going to interact with them is going to go up. And as a result, that's going to make it so that the resistance of the material itself is going to increase. So, how much does it increase? Well, with conductors, the relationship is relatively simple. Over kind of a reasonable range, if I want to plot the resistivity of a conductor as a function of temperature. And why do I do resistivity? Well, resistivity is a quality of the material itself. We learned last time that resistivity was something you can look up in a table, and you could figure out what the resistivity of different materials are that way. Over a reasonable range of temperatures, the relationship between resistivity and temperature for conductors is basically linear. Okay. Now, it's not linear over massive ranges. If the conductor gets to be, let's say, really, 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 really hot, it might melt. Okay, so if your conductor is copper and you apply enough heat to it, then it eventually will melt. And this type of relationship isn't really going to probably apply anymore, although I don't know exactly what would happen at that point if you tried to pass electricity through like molten copper. I don't know much about how that works. But basically, over some range of temperatures, the resistivity increases as the temperature increases. And if you want to turn that into an equation, you can make an equation that looks just like this right here. Okay. To gain some understanding of what this equation says, we can look at the terms. It says the resistivity as a function of temperature is equal to the resistivity at some reference point multiplied by 1 plus alpha, which is what we call the temperature coefficient of resistivity. This is a number that we can also look up in a table. It's going to depend on what the material is. And then you multiply by T minus T naught, the temperature at which you want to measure the resistivity minus the initial temperature. Easier way to understand where this comes from is to think about this graph right here. So if I pick 2 points on this graph, so let's say that I pick this point right here and I pick this point right here. If I know what this one is, let's say that I know that this right here is what we call rho sub naught. It's the resistivity at some reference temperature. And I'm trying to calculate what rho of T is. The resistivity at some temperature that we just call T. So this is T naught, and this is T. Really all you need to know to get from this value up to this value right here is the slope of the line, right? So if I tell you that the slope of this line is equal to alpha, then I could write the expression down that alpha is equal to what? Rise over run, right? So the rise would be rho of T minus rho naught divided by, I don't know why I put an extra parenthesis on the end there, rho of T minus rho naught divided by T minus T naught. Which, if you want to, you can basically convert that into this equation right here. You can just play around with it. Multiply the bottom times alpha, you get this term right here. And then you need to solve for rho of T. So you add the rho naught to the left-hand side. Wait a minute, does that work? Confusing myself. If I multiply this over, I would get alpha times T minus T naught is equal to rho of T minus rho naught. You would add the rho naught over here.
There should be a rho naught by the alpha.
Yeah, it doesn't work out, does it? Because then there's not a rho naught here.
Mm-hmm.
So I guess what that means is that maybe rho naught times alpha is what the slope is. Rho naught times alpha. Why does rho naught show up over here? Oh, so alpha is measured in degrees Celsius inverse. That's probably why. Because if this is just degrees Celsius inverse and I multiply by this, I'm just going to get a unit. So this piece...
Are we trying to find slope dimensions?
Yeah. So I guess what we would say is that this is actually not alpha. This is just the slope. What I set up here was wrong. Then this would be the slope m. And so would this. And then what has to happen now is you have to factor out rho naught from the left-hand side so that it becomes 1 plus m divided by rho naught times T minus T naught is equal to rho of T. That'll work as long as m over rho naught is what you call alpha, right?
That looks better.
That must be what happens. You know, I guess I've never worked this out before, or if I did, I didn't realize that doesn't actually work out. So I guess this is actually what the slope needs to be. Does that give you the right units? Let's see. The slope would have units of resistivity over temperature. So then if you divide by resistivity, you get temperature inverse. So that works out. Yeah, okay. So, all right. So it's just been kind of written in a slightly different way. I guess you could have done it. You could have written your equation like this, where your slope would be. Yeah, okay, that makes sense. Anyway, so you get this expression, and we can use it to kind of solve for what the resistivity is at a certain temperature. So we are going to use that to solve a problem, but I'm going to mention one other thing here, which is that we saw in the last lecture that there's a connection between resistivity and resistance right here. Resistivity is a property of the metal itself, but resistance is, if you take a particular piece of metal and you give it a certain length and a certain diameter, you can calculate what the total resistance of that metal is. And the relationship is that resistance is equal to rho times L over A. So since resistance is directly proportional to resistivity, you can also write an equation that says resistance as a function of temperature is also equal to the resistance at some fixed value multiplied by 1 plus alpha times T minus T naught. So you get this exact same equation for resistance as you do for resistivity because they're directly proportional to each other. So let's use that second equation to apply to this calculation right here. It says the temperature dependence of resistance. It says suppose the resistance of a copper wire is 1.05 ohms at 20 degrees Celsius. So that's going to be our R naught, 1.05 ohms. It says to find the resistance at 0 degrees Celsius and at 100 degrees Celsius using alpha equal to this for copper. All right, so we're going to find the resistivity at 0 degrees Celsius by plugging in 1.05 ohms multiplied by 1 plus alpha, which is 0.00393 degrees Celsius to the negative 1, multiplied by, and then you have to do T minus T naught, so 0 is the temperature we're looking for, minus T naught was 20, the temperature that this one was measured at, 1.05. And you get that the resistance at 0 degrees Celsius is going to be equal to
0.967.
0.967. Okay, and then the units are of course going to be ohms.
Ohms, yeah.
Does anyone have any questions about that? It's pretty easy. These problems are pretty easy. And then resistivity at, what do we want to do, 100 degrees Celsius? Now don't think that just because you have this equation that you can just plug in 1,000,000 degrees Celsius and it's 1,000,000 degrees Celsius here and it's going to give you the right answer, because it won't. I think that the range over which this is true is like 200 degrees Celsius. So you basically have to stay between, let's say, temperatures that you can produce with a stove or something like that. Maybe, I don't know. Maybe that's not even right. Maybe from a range of about negative 50 degrees Celsius up to probably like 300 degrees Celsius or something like that. Okay, so
at 100, I got 1.38.
You get 1.38. Okay, let's plug in the numbers. 1.05 ohms multiplied by 1 plus 0.00. And we multiply that by, so T is 100 now, minus 20. And you said you got
1.38.
Yeah, that seems reasonable. Okay, so for the numbers that we picked here, it doesn't seem like it changes much, right? But, I mean, it matters if you're designing some type of electrical circuit, and it's going to be subjected to rapid fluctuations of heat, like if it's out in the desert, for example, and it's going to get really cold at night and really hot during the daytime. There's going to be a change of the resistance, which means any voltages within your circuit are going to be affected by that. Any current flow in your circuit is going to be affected by that. So, yeah, you know, it matters. But what's up?
Yeah, so that 0.00393 is the alpha?
That's alpha. Yeah, that's alpha. Alpha equals this. That's right. And again, that's a number that you can look up in a table. When you're doing your homework problems, there's a table in your textbook. You can, of course, also Google temperature coefficient of resistivity for metals, and you'll probably find a table. Right? Okay, so let's talk about the other two classes of materials. So semiconductors. Semiconductors are used to make things like transistors, which are extremely important for computers, and they have properties that are slightly different from conductors, and they're like entire courses you can take on semiconductors. I haven't really ever taken any, so I'm not even close to an expert on these things. But semiconductors are devices where, depending on how much you dope them, so you can add kind of imperfections to them, and it will alter their electrical conductivity. Examples of semiconductors are things like silicon, and they have kind of the opposite type of relationship here for resistivity to temperature. For semiconductors, I don't know how here. Let's kind of start a new section here. For semiconductors, they kind of have the opposite effect. When you plot the resistivity as a function of temperature, resistivity for semiconductors, at least over some small range, it's exactly the opposite. So their resistivity actually goes down as the temperature increases. Okay? So they're very different. I don't really want to talk so much about semiconductors today, as if you want to learn more about this stuff, I would highly recommend that you go do your own research, because like I said, I'm not even close to an authority on what semiconductors are. I never took really any courses with them in college, and any knowledge that I have of these is just about stuff that I've read. Okay, superconductors is a little different though. That's the main thing I want to spend the rest of the day talking about. So superconductors are really interesting, because if you plot the resistivity as a function of temperature for these type of materials, what you find is that when you get really close to absolute zero, so I could put temperature here, right? And then zero temperature would be right at the origin, right? Yeah. Okay. So superconductors, I believe, were first discovered in like the 1910s, 1920s, I believe, or maybe that's when they were theoretically predicted. We're going to look at a timeline here in a second. And what happens inside of superconductors is that electrons are still carrying charges, just like in conductors, that you still have electrons that are carrying charges. But what happens is that at a certain temperature, they have kind of a discrete change in their conductivity. So let's say that this is actually absolute zero right here, okay? And I plot the resistance as a function of temperature for, let's say we use mercury. Mercury is something that becomes a superconductor at a certain temperature. For mercury, when you get to what's called a critical temperature, and this critical temperature is going to be different for, so TC stands for critical temperature. So there's kind of like a phase change that occurs at this critical temperature, where for mercury, the critical temperature, I think, is something like 4 degrees Kelvin, which, in case you don't know, 4 degrees Kelvin is extremely cold. Remember that, I don't know what everybody knows. So 0 degrees Celsius is equal to about 273 degrees Kelvin, or we just say 273 Kelvin, okay? And the gradations on the Kelvin scale are exactly the same as Celsius. So if I add 100 Kelvin to this and go to 373 Kelvin, you get exactly 100 more Celsius too. So it's the same kind of divisions, right? So this is the freezing point of water, and this is the boiling point of water. So 4 degrees Kelvin is on the order of what, negative 269? This would be negative 269 degrees Celsius. I don't think there's any point on Earth that is this cold. even space itself. Like outer space has an ambient temperature of about 3 Kelvin, I believe. So this is about the temperature of the emptiness of space, which is mostly devoid of matter. So extremely cold temperature. A phase change occurs where the resistivity basically drops to 0. I guess I could use a different color for this line. So the resistivity drops to 0, and then above that critical temperature, the resistivity basically just starts to increase, just like it would for a conductor. Okay, and how this line looks, it might actually be curved. I don't really know. It's not really important. This is what we're interested in. The fact that at some particular critical temperature, the resistivity drops to 0. So for any superconductor, below the critical temperature, the resistance or the resistivity drops to 0. And this has some really interesting effects. So first of all, one effect is that if there is no resistance, that means that if you were to have an electrical current flowing through a superconductor, it wouldn't actually dissipate heat. And that electrical current would basically tend to just keep flowing forever, right? So in a superconductor, there's not going to be really any heat that's lost to the environment as long as you maintain it at this low temperature. Okay, and it takes a lot of energy to keep something like this at a low energy. In fact, there's a lot of things I want to say, so I'm tending to want to jump ahead. But at the Large Hadron Collider, which is a gigantic physics experiment in Europe near Geneva, they use superconducting magnets in order to bend really high velocity particle beams, and the energy cost, if you look at like the breakdown of like where all the energy that they consume to run this gigantic machine is, the vast majority of it comes from just keeping the magnets cold, keeping the superconducting magnets cold. So if you want to make a really strong magnet, you all probably know, even though we haven't talked about it in this class, that you can make a magnet by taking something like a piece of metal, like a nail, like an iron nail, and then wrapping wires around it and then applying electric current to it. You can make an electromagnet. I think that's something you were all probably familiar with. Is that right? Like that you can make an electromagnet by taking a nail and wrapping wires around it? Okay. So you can also make an electromagnet using a superconducting material, but the effect is that you get much, much, much stronger magnets by doing this, like orders of magnitude stronger magnets, right? And the only kind of drawback is that you have to keep the magnets extremely cold, or else they won't be superconducting anymore and they won't produce nearly the magnetism that you need to bend these particle beams. So yeah, that's where most of the energy cost of running the LHC comes from, is from just keeping the magnets cold. All right. Okay, so below the critical temperature, the resistivity drops to 0. So supposedly there are experiments where they've tried to kind of prove that the resistance is 0. And what you can do is you can basically take one of these superconducting materials, you can get a current flowing through them, and supposedly they have some superconductors that have had current flowing through them for like 50 plus years with no detectable loss or a very small loss of that current that's flowing inside of it. Okay, so it's really powerful.
Really?
Yeah, supposedly.
50 years.
More than that, maybe. Like I think like in the 1950s, they kind of started doing some of these experiments, and they're still running. Basically, you could just put a current inside of these things, and it'll just keep going. Now, why this? Go ahead.
I was like, oh my! I was like,
yeah, it's pretty crazy. So people talk about perpetual motion machines. In fact, I think it was brought up. I don't know if it was brought up in this class or if it was brought up in my 1A class. The laws of thermodynamics tell us that we can't actually make perpetual motion machines. That would be a machine where it basically just keeps moving and moving and moving forever. But somehow superconductors, you can at the very least have an electric current, which is a type of energy at least, flowing in a circuit for apparently a really long time. Now, why this occurs is because the charge carriers are normally electrons inside of metals, but inside of superconductors, what happens is the electrons kind of start to pair up. They pair up into something that's called Cooper pairs, And the details of all this stuff requires some quantum mechanics. So I'm not going to go into a lot of the details of that. But the point is that that when this happens, you get this stream of flow, and you get a superconductor. All right. So superconductors have a lot of interesting properties that I've already mentioned, but one property they have that's truly surprising is that they can do really strange things to when you place them inside of a magnetic field. Okay, when you place these things inside of a magnetic field, some really strange stuff happens. So I'm going to show you a video, because I don't think that I can properly explain this. But in general, what ends up happening is that if you have a superconductor and you place it into a magnetic field, the superconductor will do something that's really surprising. And to give you an idea of what's surprising about it, I want you to think about the following scenario. Suppose that I give you a magnet, okay, and let's say that I have a really wide and I have a really flat magnet. And I know we haven't talked about magnetism in this class, but I'm relatively certain that you all have a good understanding of magnetism. You understand that magnets tend to have a north pole and a south pole, right?
Mm-hmm.
North pole, south pole. You also probably know that the south poles of other magnets will be attracted to the north pole of this magnet, and vice versa. Okay, so suppose that I take another magnet that's kind of smaller than this magnet, and I place it on top. And again, we're going to use like a disk. So imagine that I take a disk that we're looking at from edge on, and my disk here is got the north end up here. No, I want to put the north to north, right? I put the north end of my upper disk up here, and I put the south end of the other disk down here. And let's say that the lower magnet is sitting on top of a table over here. Sorry, this magnet's just sitting on top of a table. And I got rid of all those lines. Whoops. And let's say that I just take with my hand and I place this magnet above the other magnet. Okay, so I'm holding it with my fingers, but then I let go. What's going to happen if I put this magnet? It's going to slide off, Delvino? Yeah, why do you say that? Why wouldn't it just sit there and just levitate above the other magnet? Repulsion? Okay, so there's a force that's going to make it so that the north end of this magnet repels the north end of this magnet here. You don't understand that. I mean, you certainly have, all of you at some point in your life, have taken two magnets and tried to push them together. If you have the same side, yeah, it's going to flip, Dehao. That's right. Delvino says it'll slide off. So basically, this magnet on top is repelled from this magnet here. And you might think, well, maybe I could just balance the upper magnet on top of this magnet. That's not what's going to happen. Actually, what's going to happen is that the magnet's going to flip like this. Is that what you said, Dehao? Yeah, it's going to flip. The magnet's going to rotate 180 degrees until the south side of the magnet touches the north side of this magnet here. And it'll basically just kind of come together. So that eventually what it will look like is basically just that the top magnet is basically going to land on the bottom magnet until the south side here and the north side's here. Okay? Or, what Delvino said might be true, if we put the top magnet too close here, the upper magnet may try to flip over, but then it may fall and land on the table over here. Okay? Those are the two possibilities, basically. You cannot get the upper magnet to stably levitate above the lower magnet. It just isn't. It just won't work. Okay? You can play some tricks, like I could put a wooden rod straight this way, and I could cut a hole in the upper magnet, and then it would kind of levitate, but it would still be kind of wobbly. All right. God, I wish we could be at the school so I could just show you these things. We have examples of all this stuff.
Yeah, that would be much easier.
But we're not, so it is what it is. So what I can do is I can show you a video of what happens. So now, what's interesting is that if instead of placing a magnet on top of a magnet, you're never going to be able to get a magnet to levitate above another magnet, unless you do some tricky things. Like, there's things you can do. Like, if you could get this upper magnet to be completely rotating along an axis like this, if you could get the upper magnet to completely rotate, then you could make it levitate as long as it was rotating due to conservation of angular momentum. So if this thing was rotating like a top, you could technically levitate it above the other magnet, although it would be very, very, very tricky. Although I've done a demo at another school where you can do this. It's possible. It's just, the point is that getting a magnet to levitate above another magnet is generally very difficult because it's like an unstable equilibrium. It's like trying to balance it's almost exactly like this. Take a pencil and try to balance it on its tip. And even try to balance it on the eraser. It's still going to be just as hard. It's basically impossible, right? I mean, even though in principle, You could get a pencil that is completely perfect, let's say. It's uniform in every way, and it's completely balanced. You would imagine that it should be in principle possible to like take your, I don't know how much you guys can see, to take a pencil and just like balance it on one end, but you know that if you try to do that, it's going to fall over. And that's because we call this unstable equilibrium. What is stable equilibrium? Well, stable equilibrium would be something like this. I place a marble inside of a bowl. The marble will always, eventually, come to the bottom. This would be stable equilibrium. The difference between the two is that with stable equilibrium, if you just place the object a little bit away from the equilibrium position, it will fall back to equilibrium. A pendulum is another example of this. A pendulum, which is a ball on a string, has a natural equilibrium point that's at the center. And if you displace it from the center, it will always return to the center. That's stable equilibrium. Unstable equilibrium would be like placing the north end of a magnet on top of the north end of a magnet. It's just going to flip over. Or if you try to balance a pencil on its end, it's just going to flip over, right? It's just going to fall over, topple over, right? Okay, well, superconductors are really strange because it turns out that you can actually levitate a superconductor above a magnet. And so that's the video that I want to show you now. I've been showing the same video on this for several years now, as long as I've been teaching. This video is from 2012. No, I think this video is from 2008, actually. I found another one that's kind of more updated from 2015, but it's not as good. So we're going to watch this one. And there are lots of other videos you can watch about this if you want to. I particularly like this one. Maybe it's because it's one of the first videos I saw that actually showed all this stuff. Okay, so let me know if you can hear when I start playing this. I don't know if you'll be able to, but hopefully you'll be able to. Let me know if you can hear this. Okay, I can't even hear it.
Nope.
So we gotta work with some volume mixer stuff real quick. All right. I think it's set up to play through my speakers, and I need to do this. Yeah, Chrome is not set up to play that way, so we want to play this through this one, I think. All right, let's try that. Did that make sound?
No.
Really? You really can't hear that?
Nope.
Yeah, we can't.
Okay, so I think what I have to do is I actually have to change windows. I'll try one more time.
Oh, there it is. You can hear it.
Okay, great. All right. I'll turn on closed captions. We'll see how good those are. Okay, here we go.
The phenomena you saw here for a brief moment is called quantum levitation and quantum locking. And the object that was levitating here is called a superconductor.
Is that better, Jacqueline? If I turn it up a little bit there.
Superconductivity is a quantum state of the matter, and it occurs only below a certain critical temperature. Now, it's quite an old phenomenon. It was discovered 100 years ago. However, only recently, due to several technological advancements, we are now able to demonstrate to you quantum levitation and quantum locking. So, a superconductor is defined by two properties. The first is zero electrical resistance, and the second is the expulsion of magnetic field from the interior of the superconductor. That sounds complicated, right? But what is electrical resistance? So, electricity is the flow of electrons inside the material. And these electrons, while flowing, they collide with the atoms. And in these collisions, they lose a certain amount of energy. And they dissipate this energy in the form of heat. And you know that effect. However, inside a superconductor, there are no collisions. So there is no energy dissipation. It's quite remarkable. Think about it. In classical physics, there is always some friction, some energy loss, but not here, because it is a quantum effect. But that's not all, because superconductors don't like magnetic fields. So a superconductor will try to expel magnetic fields from the inside. And it has the means to do that by circulating currents. Now, the combination of both effects, the expulsion of magnetic field and zero electrical resistance, is exactly a superconductor. But the picture isn't always perfect, as we all know, and sometimes strands of magnetic field remain inside the superconductor. Now, under proper conditions, which we have here, these strands of magnetic field can be trapped inside the superconductor. And these strands of magnetic field inside the superconductor, they come in discrete quantities. Why? Because it is a quantum phenomena. It's quantum physics. And it turns out that they behave like quantum particles. In this movie here, you can see how they flow one by one discretely. This is strands of magnetic field. These are not particles, but they behave like particles. So this is why we call this effect quantum levitation and quantum locking. But what happens to the superconductor when we put it inside a magnetic field? Well, first there are strands of magnetic field left inside, but now the superconductor doesn't like them moving around because their movement dissipate energy, which breaks the superconductivity state. So what it actually does, it locks these strands, which are called fluxons, and it locks these fluxons in place. And by doing that, what it actually does is locking itself in place. Why? Because any movement of the superconductor will change their place, will change their configuration. So we get quantum locking. And let me show you how this works. I have here a superconductor, which I wrapped up so it stays cold long enough. And when I place it on top of a regular magnet, it just stays locked in mid-air. Now, this is not just levitation, it's not just repulsion. I can rearrange the fluxons and it will be locked in this new configuration, like this, or move it slightly to the right or to the left. So this is quantum locking, actually locking, three-dimensional locking of the superconductor. Now, of course, I can turn it upside down and it will remain locked. Now that we understand that this levitation, so-called levitation, is actually locking, yeah, we understand that. You won't be surprised to hear that if I take this circular magnet, in which the magnetic field is the same all around, the superconductor will be able to freely rotate around the axis of the magnet. Why? Because as long as it rotates, the locking is maintained. You see, I can adjust and I can rotate the superconductor. We have frictionless motion. It is still levitating, but can move freely all around. So we have quantum locking and we can levitate it on top of this magnet. But how many fluxons, how many magnetic strands are there in a single disk like this? Well, we can calculate it, and it turns out quite a lot. 100 billion strands of magnetic field inside this 3-inch disk. But that's not the amazing part yet, because there is something I haven't told you yet. And Yeah. And the amazing part is that this superconductor that you see here is only half a micron thick. It's extremely thin. And this extremely thin layer is able to levitate more than 70,000 times its own weight. It's a remarkable effect. It's very strong. Now, I can extend this circular magnet and make whatever track I want. For example, I can make a large circular rail here. And when I place the superconducting disk on top of this rail, it moves freely. And again, that's not all. I can adjust its position like this and rotate, and it freely moves in this new position. And I can even try a new thing. Let's try it for the first time. I can take this disk and put it here. And while it stays here, don't move, I will try to rotate the track. And hopefully, if I did it correctly, it stays suspended. You see, it's quantum locking, not levitation. Now, while I'll let it circulate for a little more, let me tell you a little bit about superconductors. Now, so we now know that we are able to transfer enormous amount of currents inside superconductors. So we can use them to produce strong magnetic fields, such as needed in MRI machine, particle accelerators, and so on. But we can also store energy using superconductors because we have no dissipation. And we could also produce power cables to transfer enormous amount of current between power stations. Imagine you could back up a single power station with a single superconducting cable. But what is the future of quantum levitation and quantum locking? Well, let me answer this simple question by giving you an example. Imagine you would have a disk similar to the one I have here in my hand, 3-inch diameter, with a single difference. The superconducting layer, instead of being half a micron thin, being 2 millimeter thin, quite thin. This 2 millimeter thin superconducting layer could hold 1,000 kilograms. A small car in my hand. Amazing. Thank you.
Oh, whoops, I didn't mean to close the stream. Sorry about that. There we go. So yeah, superconductors. What do you all think about that? Do you have any comments, questions, ideas?
Cool. Professor, what did he do in the last part?
Hmm?
Like, he said, like, it can lift a car?
Yeah. Yeah. Yeah, I guess if you have a lot. So what he was saying was the piece that he was showing you was half a micron thick. God, it's hard to imagine it's that thin, but what's a micron? Do you all know?
Isn't it like a millionth of a meter?
Right.
Or...
Right. Yeah, exactly. It's a micrometer. Micron is just it's kind of shorter way of saying it. So I guess that thing he was showing you was half a micron, but he was saying that if you made it 2 millimeters thick, that you could then would be able to levitate a car, basically, is what he was saying. Yeah. So it's like Delvino saying that someone made a video Niall Red made a video on how to make a superconductor. That's cool. There are...
Yeah, I saw that, but I had no idea what that was until now, I guess.
Oh, interesting. I actually kind of want to check that out now. The materials that you can use for superconductors, there's a lot of different types, but you know, as he mentioned that you could levitate a car, you could also kind of make a maglev train, right? You know, we have these monorails that are basically magnetic levitation trains. You could do the same thing with superconductors, except they would be supposedly maybe would take less material, or maybe they would be even stronger. Yeah, like bullet trains, sure. But yeah, one of the biggest problems is you have to keep them cold. I don't know if you noticed in that video, but in the video,
Liquid nitrogen, right?
he was using liquid nitrogen exactly to cool it down. And
We need room temp.
yeah, so if you could make these things like room temperature, then you could. I mean, I'd love to hear what your ideas are, but yeah, you could imagine that you could make like a skating rink, but instead of it being a skating rink, you could make it like a hoverboard rink, where you basically have hoverboards that are made of superconducting material, and you make the rink itself out of a magnet, and then you could literally just go and you'd have like a hoverboard basically.
A sci-fi in me is kind of imagining that if we would have UFOs, that they would have these things everywhere to levitate the whole thing.
Yeah, maybe so, yeah.
Is that even viable with our energy situation right now? I mean, you're like the skating rink, but I'm like, okay, so there's like human sensory experiences, and then there's like scientific research. I don't know. I don't know if we're ever gonna get to the point where we're gonna have to like pick and choose between, but
What do you mean?
like the thing with helium.
What do you mean pick and choose?
Well, humans, they like things that make them feel good, right? So it's like helium, like, oh, I want a helium balloon because it looks cool, and it's like, oh, it's interesting.
Mm-hmm.
Versus, oh, let's use that helium for some investigatory scientific field or purpose, or so like pick and choose, like from our resources, because we have limited resources on this earth.
I mean, we have limited resources, but I think that there's still, it's not like we're gonna run out of everything tomorrow or something like that,
Hopefully, by that time where we get to that point, we'll be able to have good ideas and viable ways to try to maintain what we have.
Mm-hmm. Well, we're trying, right? I mean, I don't know. I was listening to a story yesterday about how California is supposed to be fully on renewables by 2045, and they feel like they're kind of on track for that. So, I mean, who knows? Like, we understand what these problems are, and we'll address them. You'll address them as you grow up, and you all become engineers and you design new things. You'll care about this kind of stuff. So that's how things change, right? Is that people kind of start changing their minds about what matters. Anyway, but about superconductors, what other ideas do you guys have about these kinds of things? What kind of things can you imagine that you could use these for?
Maybe cars without wheels.
Cars without wheels? Yeah, maybe so. Maybe so. I mean, frictionless motion is pretty cool, right?
Yeah, I was gonna say something with very low friction.
Yeah, I mean, as he said, it's frictionless, and I mean, you're always going to have some kind of drag or air resistance, right? But you could imagine that you could get rid of that too if you really wanted to, or reduce it. If you made like a tube that you could evacuate some of the air from, and then have your train move through the tube. Maybe that's what you do. Transportation for people and goods, yeah. But who knows what these kind of things are going to be used for, because it's a type of material that does things that are really surprising, this type of locking of magnetic fields. As he mentioned, we're already using superconductors in MRI machines and particle accelerators, some of the kind of more advanced technology that exists out there, right? And so, the sky's the limit as to what you can do with these type of things, just as far as your imagination can take it. I wanted to kind of mention that what Cam said is actually really true, that if we could find a superconductor that had superconducting properties at room temperature, it would be amazing. If it was cheap enough, we would probably replace every single one of our power lines with these type of things, because as I was mentioning yesterday, when you transport energy from a power plant to your home, there's always some losses. And if you can reduce that loss of energy due to heat, then you can make your power company more profitable, which means that probably you end up as the consumer paying probably a little bit less for your energy. There's the biggest problem is that if you wanted to have a superconducting wire connecting between your power plant and your home, at least with modern understanding of superconductors, you'd have to keep it cold. And the energy costs to keep it cold might outweigh the losses due to the transmission of the losses due to heat, right? So finding a room temperature superconductor would be amazing. So I found this kind of timeline on Wikipedia, the most authoritative of websites. And so this is kind of a timeline of superconductors. They were first discovered in 1911 by a guy named Heike Kamerling Onnes. I don't know how to pronounce that. Sounds like a Norwegian name. And then the Meissner effect was discovered by these guys. And then look at this. The theoretical explanation didn't come for 46 years by they call it BCS theory. And then we call the pairs of electron Cooper pairs after this guy named Leon Cooper. And then 62, tunneling of superconducting pairs through an insulating barrier is predicted. 86, ceramic superconductor was discovered by Alex Muller and Georg Bednorz. Ceramics are normally insulators, but a lanthanum barium copper oxygen compound with a critical temperature of 30 Kelvin open up the possibilities for new superconductors. So now most of the superconductors that we are finding now are actually ceramics. So what's the ceramic? Ceramic is like, clay pots and stuff like this, right? Then they're normally insulators, but they become superconductors at a certain temperature. So that was a really interesting find. In fact, I believe the one that he was showing you was he put the list of what it's made of, but it's also made of barium, oxygen, and then it was like ytterbium and some other things, or yttrium, I think. So there's all kinds of different types of superconductors. But the most exciting thing that happened with superconductors happened last year in 2020, when we actually discovered the first superconductor that functions at room temperature. So we're already kind of at that level. And this literally happened last year. Okay, so up till now when I've talked about this, I've always said, as Cam said, that it would be really nice to find a superconductor that worked at room temperature. We've actually found it now. Now, there is one caveat to this, because if you go read about what they did, they made it superconducting, but it had to be, it's crushed between two diamonds. So it was subjected to an immense amount of pressure in order to get it to become a superconductor. So it's not like they just found some material that you can just go and use as a superconductor. They found something that when you subject it to a lot of pressure, that it becomes a superconductor. But, this is how progress is made in science, right? It's by these little tiny steps where we kind of break new ground slowly, right? Scientific progress doesn't always happen in gigantic leaps. It more often happens by little tiny successive improvements on what we're doing until eventually we have, major breakthroughs that may have seemed impossible 20 years before that or something like this, right? So, superconductors are one of the most interesting things in modern science. It's a really hotbed of active research, and something that if you wanted to go into study material science or something like that, superconductors would be one of the things you might study. I think they're fascinating. I think this concept of stable levitation is just unbelievable. I mean, it's really surprising.
Yeah.
You just have to find some type of way to keep that material at that high pressure without, having to use diamonds all the time.
Does it lose its superconductivity if the pressure is released?
Yeah, I think so. I mean, you're more than welcome to go read more about it. The link to the article I was reading is on the Wikipedia page. And if you really want to, you can go and you can read the journal article they wrote if you feel like you could understand it. But, Yttrium barium oxide, is that what it is, Delvino? Is that what he said in the video? That sounds right. Yeah, there's all kinds of different types of superconductors.
Oh yeah, it looks like it's only just as stable at high pressures only.
Do you all have any other questions about this, or? Here's a list. So on the list, they're going to have the critical temperature here. Notice that almost all of these are on the order of like 10 Kelvin, between 0 and 10 Kelvin, basically. And these are just raw elements. This is like niobium, osmium, whatever, gallium, apparently diamonds, cadmium. What is diamond B? Let's see what that is. All really, really low temperatures here. Here's 33. C60, cesium 20. What is C? C is carbon, right? Oh, this is fullerene. This is like Buckminster fullerene. There's 39. Magnesium boron. Ooh, 95. This is probably the one he was showing, right? Because that's yttrium. Is it B boron?
Yeah.
I thought it was supposed to be barium. Oh, wait. Look, if you mouse over it, it does say barium. Yttrium, barium. Okay, so I guess YBCO is like a name for this particular compound. It looks like this is the one that has the highest. Oh, no, look. And this one has... What is this one called? That doesn't have a link. This is 135. This one's 203. Ah,
That's pretty close.
So this one is at 155 gigapascals.
Oh, it's probably the one that they discovered last year, right?
Maybe so. So gigapascal, let's see, 100 kilopascals is atmospheric pressure. So this is 1 million times atmospheric pressure, I think, approximately. That's a lot. That's a lot.
Pretty intense.
I mean, the thing is that, like, when you look at this upper list up here, and all you see is, like, 1 and 3 and 4, it seems kind of hopeless. But you get down to the bottom, you can see that a lot of progress has been made, because now you're in the 90s. And then at 200, you're now at, what, negative 70 degrees Celsius? That's a little more achievable. I mean, so... Anyway, so that's mostly what I wanted to talk about today. It's been an hour, so I'm going to stop the stream here, but we can keep talking about the stuff if you want to, and I'll be happy to answer any questions about homework and other things that you all have.